All right, ladies and gentlemen, what I'm going to do is I'm going to help you walk through on how to do the calculations for your resistivity lab, and then on top of that, how do you produce the graphs that you want. We're going to be doing this as a pretty dry run, so you might run into a few complications, but we'll see where we go from there. First thing I'm going to do is, if you followed the lab instructions correctly and your numbers came all right, you should get something similar to what we have here. So what you can see is that my diameter was held constant, but my increasing lengths, so we can see how resistance changes according to the length of our Play-Doh. What we were able to know is that the voltage going through there was 12 because they're from a power supply, and then the current recorded was 0.25. So to calculate resistance, all we're going to do is we're going to say that's going to be voltage divided by the current. Go ahead and enter, and then I'm going to go ahead and drag this down. For the second part, the second activity was going to be the same thing. So we're just going to go ahead and do that part as well. Voltage divided by current, and then here's what we got. Oh, let me see if I typed it. Oh, I did divided by 2. That was wrong. There we go. Alrighty. So what I notice here is that when I was increasing the length of my Play-Doh, we found out that the resistance also increased. If I kept the length constant, we found out that my resistance decreased. Well, that kind of makes sense if we just go ahead and look at the resistivity formula we have so far. And so resistivity is, or R equals resistivity length over cross-sectional area. So if I rearrange this formula just a little bit, what we get then is that resistivity is going to be resistance times your cross-sectional area all over length. We're going to use this in a moment when it comes to graphing, but just unpacking this a little bit, we see that if I were to increase the length of my resistor, that my resistance should also increase. However, if we were to look at the reverse of that, so for example, if I were to increase my cross-sectional area, my resistance would actually go down. And why is that? Well, if I've got a wire here, and I have a shorter wire versus a longer wire, the electrons have a further direction to travel through these two pieces of wire. So the longer your piece of wire, the further that electron has to travel, which means it's going to have more resistance moving through whatever material it's moving through. However, if I were to take that same piece of wire and have the same length, but I were to, instead of having the same length, I was to have it actually give it some thickness, you can think of, I've now given this electron more paths to go through that material. Because of that, there's less resistance. There's more paths to go, more electrons can flow more easily. And so what you get here is you notice that if we increase the length, resistance increases. If you increase your cross-sectional area, then your resistance will decrease. What do I mean by cross-sectional area exactly? Well, if I've got I'm doing my best here, if I've got a rectangular prism, and I were to chop this in half, meaning I were to take a knife and cut right down the middle. What this turns out to be is the cross-sectional area of my material makes this prism. And if we're doing a rectangular prism, it would be just length times width. If we were to look at a tube per se, so if I got a tube here, and I were to do the cross-sectional area again, well, my cross-sectional area would be a circle at that point. And then to find the area of a circle, we would just then use not 2 pi r, that's the circumference. Instead, we're going to use Now let me color this in again. We're just going to say area equals pi r squared. Okay. All right, now that I've unpacked this equation, to help us find resistivity, we're going to have to make two graphs. The first graph is where we changed length, and the second graph is where we changed area, or cross-sectional area. And we're looking at how resistance was changing. However, if I look at my equation here, in order to linearize my data, where is this A going to go on my first activity here? Well, if we're trying to find graph resistivity, what I want to do then is have my change in Y over my change in X. So we're going to do resistivity times cross-sectional area over length. And this will give me resistivity. However, this is not on the bottom. So how can I rewrite this to where my graph is on bottom? So I'm going to erase this real quick. And if I want to look at somehow writing this where I'm going to have my A, or my cross-sectional area on bottom, I can actually bring that on bottom by taking it to the negative first, or the inverse of it. And then up top, we can just have R divided by L. So if, on our second activity where we're looking at, we still want my slope to come out as resistivity, we can graph on the y-axis resistance divided by length, and then on the x-axis would just be the inverse of cross-sectional area. Okay. With that being said, we're going to use our data to produce this graph and then produce that graph, and then we'll be on our merry way. The very first thing that I do want to talk about, though, is that based on our data, our numbers might be a little bit different. But in this class, resistivity, this value right here, never changes. All right, in this class, it will never change. All right, because the resistivity of an object is constant. In the same way that density of a material is constant, resistivity of a material is also constant as well. So that being said, let's see what we can do with our information. Well, on that first graph, we wanted to have resistance times cross-sectional area. So this second one is actually going to be area, and this is going to be in meters squared. All right, so area of what? Well, we have our diameter here of our rod of Play-Doh. So this is going to equal, I'm going to do 3.14 times, well, that's diameter, so I'm going to do parentheses, diameter divided by 2. In parentheses, and then take that to the power of 2, because that's going to give me pi times r squared. We're going to go ahead and drag this down. And then if we want, we can even show some extra decimals here. Now, these should all be the constant here because our diameter stayed the same, but we're wanting to look at the y value of my graph, and that's going to be resistance times area. And so that's going to be ohms times meters squared. Okay. On top of that, so let's go ahead and let's just do that. So this is going to equal ohms times meters squared. And there we go. Might be something a little wrong here, so I'm gonna go ahead and okay, there we go. Go ahead and drag this down, and good to go. So now I've got resistance times area. Let's go ahead and try to make this graph. So I'm going to insert, make sure I'm not clicking on anything, insert chart. And on my y-axis, because we're going to choose our y-axis data first, just go ahead and highlight those. Click OK. We're going to want a scatter plot. And then on my x-axis, we're going to do, let's see what that was again, length. So so the length of my Play-Doh. And what we can see here is that so far we've got some pretty linear data, was what I was expecting. And so we're going to add the trend line, use equation, and let's go ahead and throw in the R value there while we're at it. So what did I notice here? I'm going to go ahead and actually move this graph to its own sheet, and I'm going to increase the point size of my line and my axis. Go ahead and make this and there we go. Alrighty, so here's what I can see from the trend line of my data. Let's go ahead and quickly throw in some chart titles. I'm going to hit pause in the video, clean up this graph a little bit. And alrighty, now I'm going to clean that up a little bit. What can I see? I can see that on my y-axis, I have my title, which is resistance times, my cross-sectional area. There we go. I'm just going to put CS area. That way we can see the whole thing. So we say resistance time cross-sectional area, giving me a unit of ohms per meter, ohms meters squared. And then on my x-axis, we see here we got length, which is in meters. So according to a little bit of that background, which we did earlier, the slope here would then get me resistivity, and my resistivity would be 0.392 ohm meters. All right, so let's do my other set of data and see if we get this resistivity value to be the same. Like I said, resistivity in this class should be constant, and since we're not dealing with any crazy high voltages, we should get a pretty close value. Let's try that out. All right, so we got calculated resistance. I'm still going to need cross-sectional area again, so I'm actually going to just copy this, throw it on right down here, and then do the same thing earlier. Ooh, let's see, will it do that for me? Hey, look at that. Cross-sectional area, and we are good. So the next thing I want to do is we're going to do, instead of R times A, we're going to do R divided by L. So resistance divided by length. I'm just going to do R divided by L. And so that'll be ohms per meter. Alrighty. And then on my x-axis is going to be the inverse. So I'm going to say area to the power of the negative first. So that's going to be meters to the negative first as well. Alrighty. Anything else? I think we're good. So let's go ahead and equals. So resistance divided by my length. And we're going to go ahead and just drag that on down. And then I also have the area, the inverse of the area. So I'm going to set equals that to the power of -1. Alrighty. Let's see if these values work. Just going to double check some things real quick. Area. Oh, I see a problem. My diameters was in centimeters over here, not in meters yet. So I'm actually going to fix that. And so this is going to be 0.05. That's going to be 0.01, 0.015, 0.02, 0.25. There we go. Those numbers look a bit better. Now let's try graphing this. So I'm going to go ahead and let's do insert chart. I'm going to insert my y-axis data first. So we're going to go to chart type, scatter, series. What is going to go on my y-axis? Well, that's going to be ohms per liter. ohms per length. And click OK there. X-axis is going to be, should be this range right here. Click OK. And it looks like something is a little bit off. Let's just go ahead and keep going with it and see where we can go from there. I'm going to do series, trend line, use equation, show the R² value here, which is dangerously low. I'm going to double check some of my numbers real quick. I wonder if we look at, if I take away my first data point, we get pretty close to our original number there. And so I'm actually I'm gonna go with that number. So we can clearly see here that there is an outlier here. And so when it comes to data that has an outlier, you are welcome to remove those outliers as long as you have enough data to still make your generalized statement. If I take that first one out, my data gets a whole lot more linearized and my R value goes up quite a bit. So I'm going to go ahead and move this to its own sheet. I'm going to hit pause on the video and then I'm going to clean this up a little bit and then explain what we can see. Alrighty, now let's look at what this graph is telling me exactly. I'm going to go ahead and just make these lines and the dots here just a little bit thicker so we can see what's going on. Let me choose a nice bright color. There we go. So here's what we can see is that our resistivity of Play-Doh for the second part of our lab is 0.146. And so that resistivity is a pretty low number. And for our first chart, our first graph, we thought it was 0.392. So we're going to give this discrepancy just due to some experimental error. Could be the Play-Doh, could be the consistency of the Play-Doh. But both of these graphs allow us to see what was talked about at the beginning of this overall video, was that one, resistivity itself never changes. It is a pretty constant value unless temperatures tend to get really, really hot or really, really cold. And it's looked at a couple different ways. You can look at the length of your object. We can look at cross-sectional areas and see how that affects the overall resistance. Okay, if you have any questions about this video or what this analysis looks like, please give me a shout out. If you like this video, subscribe and to hear more. Thank you. I'll see you guys next time.